In this video, we're going to talk a little bit more about minimum spanning trees. So in particular, we want to modify the graph somehow and show how to compute a minimum spanning tree faster than just recomputing it from scratch. So for all of these problems, we want to basically understand what happens when we do this modification to the graph and figure out a quick way to update it. So first, we talked about this proof using a exchange argument in class of why safe edges must always be taken in the minimum spanning trees. But there's actually a stronger statement which says for any cut in the graph, S and V minus S. So if we put all the nodes in either S or in V minus S, then it turns out that the lightest edge crossing the cut must be in the MST. So here, all the possible edges would be these three purple edges, and then E, and I'm assuming here E is the lightest one. It has the smallest weight. So in particular, we actually get this kind of optimal substructure, which says that an MST for the entire graph G is an MST for the left side, G of S. So we have an MST here in green for the left side, and MST for the right side. Again, the MST edges are in green, and the purple edges are not in the MST. And then we also union that with the lightest edge crossing the cut, which is E. So really we have this T sub S, T sub V minus S, and U, and T sub S with T sub V minus S with E gives us T. And this will always be true. And why is this? Well, it's basically because the weight function's linear. So remember, the weight function of a tree is just the sum of every edge on the tree. And so naturally, you can split this into the sum of things over here, the sum of things over here, and the sum of this, just by moving terms around. So in particular, the weight of the tree is the weight of the things in the left tree, the weight of the things in the right tree, plus the weight of the edge connecting them. So that's kind of why we get this optimal substructure, but the important part is it's true. So if you could compute a minimum spanning tree for both sides, you can then connect them with this lightest edge. So you could essentially come up with a recursive algorithm to do this. And that's almost kind of what most of our algorithms are doing. So you get the same running time you'd get as if you did a just straight up recursive algorithm. That's why that log term is there. So essentially, we're doing n over 2 work, and then E work to scan these edges, and so we get E log V. But now, the reason I'm telling you about the optimal substructure thing is because it'll allow us to do these fast. So let's first look at part A. So this says we changed the graph by taking one edge on T and decreasing its weight. And now the question is, what's the new minimum spanning tree? So for example, let's say this weight was originally 10 and now it's 5. Well, obviously, that's still going to be the lightest edge here. We just took the lightest edge and made it even lighter. So the tree doesn't change at all. So for part A, T is still the MST. And remember, as long as the edge weights are unique, the minimum spanning tree is also unique. So that's why I said the minimum spanning tree, not a minimum spanning tree. So that's the first case, part A. And so how fast can we do nothing? Well, we can do this in constant time, basically. But if we technically need to look at the tree, then it's linear. Either way, it's faster than E log V. Now, part B, we have that an edge off the tree is increased. So here, one of the purple edges, let's say originally was 15, well, this is now 20. Well, we didn't want to take that edge before because it was too heavy. Now we've made it even worse. So again, we don't have to do anything. So really easy. So now let's look at C. So in this case, one edge on T is increased. So now this one is a problem. So now, maybe it's better to have a completely different edge. Like maybe this no longer is the minimum spanning tree. Maybe something else would be better. Now we could recompute the whole minimum spanning tree, but the point of optimal substructure says, well, we already know what's optimal for these two sides, and we don't need those to go to waste. The only change that could happen is in this little valley here. So although E might be worse, all we really need to do is look at all these edges, and the lightest one will give us a total minimum spanning tree based on this structure. So in this case, we know the part of T on side S and the part of T on side V minus S are still optimal. Just need to fix E. So in particular, what we need to do is find the lightest edge crossing the SV V minus S cut. Now up to this point, I've been leaving it kind of vague what the SV minus V cut is. So really what this is, S is going to be the set of nodes. So this is the reachability set of U. So remember E equals UV. So this is just the reachability set of U in the tree T minus E. So basically we remove E from the graph, or from the tree, and then we compute everything reachable from U, which will be everything colored in the left side. So that's what T sub S really is. So this is the same thing as, this is basically T sub S that we were talking about before. And similarly, so that's going to be S, and then V minus S is just everything else. So those are the two node groups. So now how do we find this? Obviously we do an O of V plus E, whatever for search, to find the reachability of U, and it takes like constant time to subtract E from T. So the next thing we need to do is find the lightest edge crossing this cut. So how do we do that? Well, now that we know what the cut is, well, we can just check. We can check every edge that leaves one side and goes to the other. So now can compute all edges crossing the cut. And so just need to scan the set and pick the cheapest one or the lightest one. So we're scanning a set of edges, so that's going to be OV. Now, how do we actually compute all those edges crossing the cut? Well, you can really do it by doing a search, like a DFS, and while you're doing it, just check, did we just find an edge that goes from something in S to something not in S? And you could do that by keeping like a marker, v.s or v.not.s. So let's call it v.m for membership. That's either S or it's v minus S. So that's one way you could do it, but I'll leave that detail as an exercise. But you can do it efficiently. And then that's it. So the final spanning tree is just going to be everything on the left, everything on the right, and I'll call this lightest one E prime, which could still be E. Maybe nothing actually changes, but either way, this is the new MST. And so in total, we do O of V plus E. Cool. So now in the last case, which is the hardest one, we have decreased an edge off of T. So in this case, one of these purple edges got smaller. So in that case, we might actually want to add it to the tree. But now it's really unclear how we will actually do that. So what we can do, though, let's just add it to the tree. So we're going to take our tree, we'll add E to it, and it's a well-known graph theory fact that if you add any edge to a tree, this forms exactly one cycle. So we'll use WFS or just the DFS with cycle detection to find the cycle. C. Now what do? So we found the cycle. And we know this edge E got decreased. So one thing for sure is the heaviest edge on this is not necessary. So we know we don't need the heaviest edge. So what we could do is just scan all the edges on the cycle and remove the heaviest one. So let's say E prime is the heaviest. Then we can take T, add E, and remove E prime. And call this new tree T prime. And I claim T prime is an NMST. And if so, then obviously this took O of V plus E time because we computed a cycle and then just scanned edges on the cycle to find the largest one. So this is max weight. So it's kind of clear that we don't want the max weight edge. We can just remove that one and it's still a tree. So if we remove this, that's still a tree. Or it becomes a tree, it's still connected. But what's not clear is why that's the best choice. And I'll leave that as an exercise, but the reason again is optimal substructure. So if you just looked at the cut involving E and E prime, so you could look at this cut that crosses like that, then optimal substructure implies you should take E over E prime. And that the optimal tree for either side was already fine. And the optimal tree for either side were the originals. So we didn't have to modify anything. So that's the idea. So that's how we can do all these simple operations without recomputing the whole MST. And it relies critically on this more general notion of optimal substructure over just simple safest edges. And that property is also proved in the book, by the way. The proof of safe edges must be included is actually also a proof of that stronger statement. So if you want more details on why that's true, you can see it in the book. Okay, so here's another problem. Here we want to compute a minimum spanning tree in linear time instead of E log V. And the benefit here is the weight set is really limited. So instead of having any arbitrary weight, we're limited to these 3 items. So how are we going to do this? Well, we can just modify Prim's algorithm. So the hard part about Prim is that we need log V time to update keys in the priority queue. But now we know there's only 3 options. So we could keep 3 separate lists of nodes that were basically the queue. So now the queue turns into 3 separate lists. One for weight 1 nodes, one for weight 10 nodes, and one for weight 25 nodes. And so now what do? We always prefer the lower weight nodes. So when we do like a pop, we always look at the lower weight list first. And so that's simple. We're just doing queue operations, but on one of 3 lists. And now doing a decrease key is not log v time. It's easier because we can just move the node from one list down to another. We don't need sorting. So whereas the priority queue would have to keep resorting things to maintain everything is in the right order, we just have to do a simple move from one list to the other, and that's implicitly doing the decrease key. So maybe it's from the 25 list to the 10 list, for example. So overall, this will decrease the running time from log v to constant overall, and so this will end up giving us a linear time algorithm. So I'm not going into the full details of exactly how it works, but this is the idea, and I urge you to think about these details more thoroughly.